In this lecture, using the disk method, we derive an integral formula for the volume of a solid of revolution. To describe the solid of revolution whose volume integral we are to find, we generate the solid of revolution by rotating a region around the x-axis. The region is bounded on the left by the line x equals a and on the right by the line x equals b. It is bounded above by the graph of f of x equals y. It is bounded below by the closed interval from a to b on the x-axis. Let us call this region region R. The graphic on the right shows how the rotation of region R around the x-axis generates the solid of revolution. We look at the solid from different angles. We will use the method of parallel plane sections to get the disk method integral formula for the volume of the solid of revolution. As the name suggests, in this method we use parallel planes to slice up or partition the solid into segments or sections. In the method of parallel plane sections, we can choose any orientation for the slicing planes as long as they are mutually parallel. For the disk method and a solid of revolution obtained by rotation of a region around the x-axis, the parallel planes should all be perpendicular to the x-axis. Getting the parallel plane sections is exactly like slicing a loaf of bread. We aim to find or approximate the volume of each of the sections. To simplify the derivation, we use approximate volumes for the different sections. The graph of f generates the lateral side of each section. The lateral side of each section is the orange shaded ring wrapping around each section. Instead, we use sections whose lateral sides are parallel to the axis of rotation, or to the x-axis. In effect, each section will look exactly like disks. A disk is simply a cylinder with a small value for its height. To generate these disks, we partition the interval from a to b into n subintervals, using the strictly increasing partition points or nodes x sub 0, x sub 1, all the way through x sub n. We set x sub 0 equal to a, and x sub n equal to b. Each subinterval determines its own disk. Suppose that we have the ith disk or section on the right diagram. This section must correspond to the x interval between x sub I minus 1 and x sub I. If delta sub ix is the thickness of the ith disk, then delta sub ix equals x sub I minus x sub I minus 1. Let V sub I be the volume of the ith disk. Then V sub I is equal to the area of the cross-section of the disk times the thickness of the disk. Let the cross-sectional area of the ith disk be A sub I. Since the thickness of this disk is delta sub ix, V sub I equals A sub I times delta sub ix. Each cross-section is circular, and so A sub I is pi times its radius squared. We use the cross-section at x sub I because it is convenient to illustrate on our graphic. And so the radius of the cross-section is the y value f of x sub I. Therefore, V sub I is equal to pi times the square of f of x sub I times delta sub ix. It is well and good that V sub I is in terms of x sub I because delta sub ix is in terms of x. This is the approximate volume of just the ith section, and there are n of these sections. So we add up all the v sub i's and find that the volume of the solid of revolution is approximately equal to the sum from I equals 1 to n of pi times the square of f of x sub I times delta sub ix. We now have a Riemann sum for the volume of the solid of revolution. If f is continuous on the closed interval from a to b, and if the maximum thickness of all the sections tends to 0, this Riemann sum should tend to a definite integral. And that definite integral is the integral from a to b of pi times the square of f of x. We factor pi out from the integral so that the volume of the solid of revolution is pi times the integral from a to b of the square of f of x. A variation on the problem is if instead of having the interval from a to b on the x-axis as the lower boundary of the region R, we have the graph of another function g of x equals y as the lower boundary. We require that f and g be both non-negative, with f of x being greater than or equal to g of x on the interval from a to b. Let's give the name R sub 1 to the region between f and g on the interval from a to b. Observe that rotating R sub 1 around the x-axis, we end up with a hollow where there was none before in the middle of the solid. Now each parallel plane section corresponding to this solid of revolution looks like a washer. Hence the term the washer method. By rotating the graph of g around the x-axis, the graph of g generates the outer lateral side of the hollow in the solid. So to find the volume of the solid with the hollow, we first find the volume of the solid generated by f. Then we take out the volume of the solid generated by g. The volume of the hollow or the hole equals pi times the integral from a to b of the square of g of x. Therefore, the volume of the solid with the hole is pi times the integral from a to b of the square of f of x minus pi times the integral from a to b of the square of g of x. Since the two integrals are over the same interval, we can combine the integrals into a single integral. Therefore, the volume of the solid with the hole is pi times the integral from a to b of the quantity the square of f of x minus the square of g of x.